Any question on this one? Okay, so we can do the locust. Locust, you guys want to do the collision avoidance, or should we go to multisensory integration? Locust I have discussed, huh? Yeah. Cycling, that's fine. That in the TEDx talk, this was locust. Yeah, I think let's go to multisensory integration. Okay. Yes. Correct. This is no recombination. So this is just the electric field. Yeah. Yeah. Well, it depends on what exact modeling we are talking about. We can talk about the modeling part, in more details later. But I think this is a way simpler modeling. You just create the geometry and you just want to look at the field distribution. This will probably not require you to look into any recombination model or anything. Never. First is experiments, then comes simulation. Yeah. Okay. Very rarely we first do simulation and then go ahead and make devices. Never. We go ahead and make devices. If it doesn't work, we forget about it. If it works, we make it better, and then if required, let's say the reviewers ask, okay, can you do some modeling? Then we do the modeling, because experiments is the ultimate truth, right? So, okay. So let's now look into multisensory integration. It's kind of inspired by Octopus. And the reason for that is, Octopus is one of the most intelligent underwater aquatic species. It navigates with two information. One is the tactile information. Its entire body is actually touch sensors. Like the catfish's entire body is tongue. Its entire body is actually it has actually distributed intelligence. So generally, in human, the intelligence is all in the brain, but in case of octopus, the intelligence is everywhere. Okay, even every arm of an octopus is a brain. Okay, so it's a very unique species, and it navigates in underwater environment with the help of both the tactile information that it gets from its tentacles, and it has a polarized vision as well. Okay, so it is very good in detecting light. Even in a very dark environment, small amount of light it can detect. But anyways, we derive the inspiration from there, but we show the importance of multisensory integration. And let me first define what does multisensory integration means, because today we are in this era of Internet of Things, right, which is literally all the sensors which are distributed around us, and then all the sensors are sending some information to a processing unit, central processing unit, right, and then processing unit kind of makes some decision about whether to light on the room, or whether what is the weather outside, whether you want to have some coffee, right? So or let's say for example when you are driving a car, all the autonomous cars, right, they are getting a lot of information through optical sensors, acoustic sensors, right, and then they're deciding whether to speed, whether to brake, right? So this is what is happening, right? This is called the sensor fusion technology, right? So you are not only relying on one sensor, but many sensors and fusing it together using a central processor, right? And if you think about us, right, we are also something like that, because we gather information not only from our eyes when we are watching, let's say, movie. We are not only looking at the visual scene, but we are probably also looking into the ambience, where we are sitting. So every information impacts our decision making, whether we like something or we do not like something, right? But in this sensor fusion technology, the sensors talk to each other. Okay, they never talk among themselves. They always talk to a central processor. Okay, this thing has not started yet. This is we call the cross-sensor modulation. This is something that happens in our body all the time, and that's why when you have information from one sensor to the other, you can only add them up, and 1 plus 1 can only be 2 or less than 2 based on how much information you are losing while transmitting this thing, right? But in nature, that is actually not true. Okay. 1 plus 1 can actually be much, much greater than 2, in certain instances. That's what I'm going to tell you. So integration is what? Addition, right? And never can we add two things to become more than either one, right? I mean, so what we will show you is that the response, this is called super additivity. This is a feature of multisensory integration. Let's say your visual gives you this much response and tactile gives you this much response. If you add these two, you should probably get somewhere up to this. But actually it goes up, almost, exponentially. Okay, this is what we call super additivity. That's a feature of, multisensory integration, and we'll see that. Okay, so where is multisensory integration useful? That's the question we need to ask. Why in nature this exists? Why does it help? Okay, so here, let's say for example, if I show you this picture, okay. So let's say I ask you to enter a room, and that's, let's say, an auditorium. It's initially completely dark, but if you enter that room and if you have no information about whether it's an auditorium or not, how will you navigate? Right? No, you can by touching, right? Because it is completely dark. So you will use your tactile information to see, if there is something in front of me, whether I'm going to topple or not, right? By touching, correct? But if for a very short period of time, if I show you this, like light comes and goes, right? Will it make your life easier in navigating now? Correct? So a small spark of that information, which is a visual information, because you see something, now even if the room is dark, you can navigate better. Correct? So what happened? What happened here is, if it was a typical robot, which does not remember anything, it will have the same difficulty in navigating whether there was a light spark or not. But in our case, it is not the case, because we have a visual memory, and now it is easier for us to navigate. You see this part aspect? This is multisensory integration, because this has a lot of these benefits, and this is what I'm going to show you. The other important thing is inverse effectiveness effect. What does it mean? That let's say if the light is completely on, right? Will you take help of your tactile sensation to navigate anymore? No. You can properly see, you will just simply straight walk and go and sit on a chair, right? So it is important when one of the information is very weak, correct? And that is the case we mostly care about. Let's say, for example, if you're walking in a forest, right? If you're walking in a forest in a complete, during the night time, you will be extremely cautious about the sound information, right? Because you don't know whether it's a, some tiger, snake, or whatever is there. So you'll be very cautious, right? Because your optical information is not there. But if you're walking in the daytime, you are not that afraid, or not putting a lot of importance on your hearing capability, right? But if you are walking in the complete darkness, you are focusing both your eyes as well as your ears are putting effort in order to make the information, amplify, so that you are not losing your life, right? Right? It's an evolutionary process that gives these two properties: super additivity, but super additivity only when the cues are weak. When the cues are strong, I don't need to add them, correct? That's why the effectiveness goes down as the strength of an individual cue becomes strong, because then that removes resources that your body needs to spend. If you need to spend resources both on eyes, both on ears, energy is being consumed, right? So this is another feature of multisensory integration. Yes, now we are going to look into this multisensory integration, how to achieve that using our devices, right? So we are using, again, our favorite MOS2 transistor. We have already shown monolar MOS2 is a good photodetector, but now it is not good for touch sensation. Okay, so I have to bring in something else, and the something else is what we call a triboelectric nanogenerator. Okay, this is an entire field in itself. This is nothing. So if you create, this kind of a structure, Captain aluminum and air, you see it's a metal, and there's a lot of charges over this surface. So when you touch, these charges actually pass, when you touch it physically, and that actually creates a voltage. So, by touching, you can generate voltage. That's why it is called a triboelectric nanogenerator. The voltages that are generated are actually, nanovolts, very small voltages are generated. But this is another way of energy conversion. This is actually an energy conversion device. right? You're converting touch energy into electrical spikes. Right? That's what your body is also doing, your skin is doing. Your touch sensation gets converted into this thing. And then you see that I have created these 3 different types of, by which I am touching, because the strength of the touch is important, right? If I touch it, gently versus if I touch it very strongly, is going to make a difference. Let's say, for example, you are in dark and you are inside a museum, right? Now you want to navigate in dark. Will you do something like this, or will you be very careful? Very careful, right? You will be doing a very soft touch. But if you do a soft touch, the information that you get back is also very minuscule, right? So we have to also, that's why I'm saying, when the cues are very weak and you are trying to navigate, how do you do it, right? How do you navigate in a museum in dark condition, right? And this is going to be very important mostly for army application, because you're already thinking, why do I care about moving in a museum at dark? I mean, I'm not that English movie where, someone was stuck in this museum for a night, right? What was that movie? Night at the Museum, right? This is very good for the army because, there might be mines and everything, and you're trying to navigate in a forest. You do not know whether there are terrorists or anything, right? So you have to be extremely careful about what you touch, right? Something blows out, then you're done, right? That's why it is important. This is just a, demonstration to use for those applications, then deriving inspiration from nature. So now let's see what happens with just the tactile response. So you see, whenever I touch it, right, I will create a voltage, and this voltage is kind of connected to the back gate of the transistor. So what I will do is I will get the spikes. Right? Every time I touch, I will get a spike because this will generate a voltage that is applied to my gate that will allow my current to flow. So I get a spike, right? And based on how strong the touch is, I get higher magnitude of spikes. So that is literally converting the touch information into current, right? And the strength of the touch is kind of characterized by the amount of current that I'm getting. Clear, right? So now the next thing is, instead of having a single touch, if I want to add 2 touch, it should be additive. So 1 plus 1 should be kind of 2, right? And that's what we show. So instead of T1, if I have T1 plus T1 both at the same time, it adds up. So if I now simply wanted to plot, this is called the unisensory integration. So compared to 1 touch, the 2 touch is just double the strength. Expected, no problem. Right? So unisensory integration does not have this super additive property. That's what I'm trying to get. It's just additive. Okay, no problem. But we can make our device a touch sensor, okay, by integrating it with this triboelectric nanogenerator. Now let's look into light. Right? So if I have light in dark, there is no response. And then as I increase the illumination time, right? For example, if I show the room for a shorter time versus a longer time, so response will be better, right? Because you have seen it for longer. So that's what is happening, right? So visual cues, as it increases, and he said the cues are characterized by the duration, my light, the current increases. Okay? And I can do the same thing, right? I can do once or twice, right? And it is also kind of additive in nature. You can see the double is actually twice the single. Right? So again, I did not achieve any super additivity just by adding the same cue. And it should not be the case, right? I mean, if I'm adding the same cue. But now what happens if I do that both at the same time? While I'm touching, I'm also putting a little bit of light, right? That will be multisensory integration because both sensor information are now coming together, right? And then if I do that, okay, this is a plot. I kind of design a quantity. So you can see this plot. These plots don't tell you much. So what I'm showing you over here is that the visual intensity is increasing and the tactile intensity is also increasing. So I see an increasing trend, no problem. But then I define a quantity which is this multisensory integration factor. What is the visuotactile response? That means both the senses are there, and divided by what is the response when only one of them is present, right? And that ratio will tell me if it is greater than 2, then I have achieved superadditivity. Electrical response. This is the electrical response, the current response, right? Is when both are present. Only visual plus only tactile. That's separate. That's what your current sensors do. Visual comes, tactile comes, it adds. But now we are adding those 2 things because this is interacting using a single device. Because the tactile response and the visual response are acting on the same MOS transistor, right? And if I do that, then you see that when look at the numbers, the addition becomes 30 times more than just adding them together, right? And that is something we could do because of this nonlinear characteristics of the MOS2 transistor, and we are operating it in the subthreshold. So whenever there is a touch, there is an exponential change in the response, right? And you see, more important thing is that T1 is a weak signal and V1 is a weak signal. And for them, the integration factor is the highest, which means when the Qs are weak, my multisensory integration is best. And when I have T4 and V3, there's a very big touch and a very big, visual cue, no multisensory integration because I don't need it, right? So this is the inverse effectiveness effect. Remember two criteria, super additivity and inverse effectiveness effect. And this is going to be extremely transformative when you combine sensors together. Make sense? Right? Because you don't care when the cues are, the information is very strong. You can make decision based on either the light information or the tactile information. When both are very strong, weak, if you just add them, you still don't get it unless you amplify it in such a manner, right, that it becomes detectable. So this is a very different principle compared to the sensor fusion technology that we use today. And it can only be done if we start the integration at the device level. You see, because we did not, we did not use a photodetector and a tactile sensor separately. We combined it, we fused it, right? So this is the ultimate sensor fusion that you can do, and that's what the biology does all the time. Right? So that's what this thing is. And then you can actually, this is, I'm going to go very quickly. This is actually a crayfish. This combines three information. Okay, it combines tactile, visual, and chemical. Okay. I will probably remove, will not go into detail of that. Here actually you have this tactile neuron being controlled by both the visual neuron and the chemical neuron. So even better in terms of integration because three senses are coming together and you can achieve the same thing, the super additivity in a system like this. This is a separate paper, you can read it, and the inverse effectiveness effect. So here we have combined three. You have seen this picture earlier today. This is a graphene chemisensor. This is a triboelectric nanogenerator, and this is a MOS2 photodetector. So now fuse these three things together. Okay, I will just show you the circuit because here what we are doing is, here is the photodetector. In the previous example, we just added the tactile sensor to the gate, right? Now we are applying this graphene chemisensor information, converting it into some voltages, and also applying that to the gate. Okay, this is a little bit more involved circuit. We don't need to go into the details of this. If you are interested, I can talk to you about that, later. Okay, but you see, when you fuse things, it has to be at the very device level. It cannot be separate. Okay, that's the the take-home message from this slide. Okay, this is our setup. So don't worry about that. You can see you have the light, you have the chemical, you have the touch, everything, and then you fuse it together for the sensor fusion technology. I think I will just skip this. Okay, this I will come back to later when we talk about maybe the multisensory thing. So the same effect is seen actually. Okay, so I'll just skip these slides for the time being. And this is what I am going to show you here. You see that I was talking about again this. Let's say you have a surge vehicle underwater, right? You see the detection limit becomes way further when you combine tactile, chemical, and visual information. That's what the crayfish also does. If you have any one of this, you never achieve such a huge radius of detection. It simply makes your detection much easier when you combine the cues together. Okay, so that's what I'm kind of alluding to over here. Okay? Easier. Detection becomes easier. Okay, because you're combining multiple information, right? Because if you have a ship wreckage or something you're trying to find, there might be some oil spill. That's a chemical information. Right? There might be more fishes around. That will give you more tactile information because the water will be more turbulent over there. Right? And then if there is some flashes of light in a surge vehicle, you can also maybe see something. But if it's only one of this, it becomes more difficult to search. See? So that is a key idea. right? It will become more effective, right? And then I think these are the the summary. That's the key parameter. That's the key parameter. What is the integration improvement that I am getting versus all working together? That's the ratio. It could be like 30 times. 30 times, right? That's quite a big improvement in terms of this, right? So this is what we showed, light to electrical, because that's what the brain is, right? Everything is converted into electrical signal, and then you combine, right? Using specific circuits. So here there's a lot of circuits involved as well. We did not talk about circuits, but you design those specific circuits to perform this, more complex task. But these two papers, if you read, both published very recently. One was in Nature Com and the other one was in Nano Letters. You should get a full picture of this multisensory integration. Good? Okay. What is next? What do you guys want to know next? Let me see. Yes. Yeah, tell me. Yeah, exactly. Exactly, yes. Happens all the time in biology, because biology is very adaptable. It kind of retrains things, neurons can make new connections, which is not possible with solid state devices. Okay. The next topic that we might be able to do is, let's see, we can cover. So how much time do we have? 25 minutes we have, right? Okay, so if I have 25 minutes, I could do this one. It's a little bit different topic, related to neuromorphic though, but emotional intelligence. That is something we can talk about. Okay. It's just not artificial intelligence. We are now getting into a very debated domain of emotional intelligence. If we are not already happy with our machines being artificial intelligence, giving emotions to them. Okay. Just 2 minutes, I will start. Papers are there, yes. If you go to this nanolator paper, the entire circuit is there. It will just take me a long time to explain those circuits. So we have not really, I don't think everybody has a circuit background here. So that will be really difficult for them to, I think, grasp. Some circuits are going to come here. These are like much simpler circuits because that is a little bit more involved circuit. You really need to understand it pretty well. The circuit that I'm going to show over here is actually quite simple. Okay, so should we start this one? Everyone is here, right? Okay, so this is again, as I was mentioning yesterday, we are trying to design a bio-inspired gustatory circuit, okay, for mimicking both the psychology and the physiology of feeding behavior. Okay, because as we were talking about sensor fusion and better decision making, right? So machines always makes decision based on logic, right? But we human beings don't always make decision based on logic. Emotion is equally involved in our decision making process. For which sometimes we make the good decision, right decision, sometimes we take terrible decisions, right? So if you really wanted to think about an artificial general intelligence, right, you'll probably wanted to integrate emotional intelligence to that as well. Where it will lead to, I don't know. Okay, don't ask me that. I hope that I will not survive to the date that the artificial intelligence becomes so emotional. Or it might be a good thing, right? So we do not know. As I'm saying, we do not know whether it's going to be good or bad. But I mean, scientific discoveries are never driven by whether it's going to enable something good or bad. You just do it. I mean, the atom bomb was not made to be dropped on the Hiroshima or Nagasaki, right? Okay, so I think let's see, how we can design that. The reason for that is, I mean, this is the current day robots, right? I mean, that kind of makes a decision based on logic, but the technology tomorrow should probably look like this, okay? And the main reason for that is what distinguishes the artificial intelligence from the natural intelligence is that we have two parts of the brain, right? We have one of the hemisphere which generally takes logical decisions, right? But then the other part of the brain is actually very colorful, okay? It doesn't take decision based on logic, right? That is where all the is there. But if you think about chemically, the two parts of the brain are exactly similar. The same neurons, the same synapses, right? It is not that there are separate types of chemicals on two parts of the brain. It's even the same neurotransmitters, dopamine, serotonin. So they're not different, right? But yet, the whatever information we get in, it goes to both parts of the brain, right? Because that's how the final decision is made, right? And one part of the brain is purely, the physiology, correct? The other part is mostly to deal with psychology. Right? And this field of psychology will actually have a lot of importance going forward. And this is actually also related to a lot of human health, right? And I mean, this part of the brain has been mimicked by this artificial neural network, but there is really nothing mimicking the psychological part, correct? And that's what we are trying to kind of match. Now let's take the example of feeding, because I mean, this is a huge space. When we talk about decision making, in what context are we talking about, right? So let's take a very simple example, because we need to understand the brain circuits which are responsible for our emotion, or can we represent emotion with some neural circuits, because at the end of the day the brain is only electrical spikes, right? So now let's think about feeding. When do we feed? When do we feed? We feed when we are hungry, right? So hunger can be a state variable. Let's say it's H. So whenever my hunger is high, I will feed. But I will also feed when I have some appetite or liking, right? For example, if I give you a rasgulla at the end of your food, you might be full with having the biryani, right? But even after that, if I give you a brownie or a cheesecake, थोड़ा खा लेते हैं, हाँ? That you are eating not because you are hungry, that is because you like it, right? After biryani, if I give you a Kerala, will you eat? No, right? But then let's say if you are completely hungry, biryani नहीं है, सिर्फ करेला ही है, you will eat, right? So therefore there are two things, and this appetite is really your psychology, right? So that determines feeding. If I now want to build a circuit that takes into account both the emotional and the logical aspect of the brain, what will be the truth table? Because that's how we make circuits, right? We have to make a truth table, right? This is just an example with this broccoli and pizza. My student liked it, and that I told you that he was presenting in a comprehensive exam, and this professor was a little bit fat. He could not go, and there was pizza being served in that comprehensive exam. He could not go and take the pizza after seeing this. Okay, so and then we feed, right? So feed is the output variable. The input is the physiological state and the psychological state, and the decision is whether I want to feed or not. Right? So we have to put it in a mathematical format Otherwise, I cannot design the the solid state circuit, right? So now let's see what will be the truth table, right? If hunger is 1, that means I'm hungry. I don't care about my liking or disliking. I'm simply going to eat it. That means I'm going to feed, right? But if I am not hungry, then I will only eat if I like it, right? So this is the truth table, because that's the first step of designing a circuit. You make the truth table. That's the don't care condition. Reminds you something, people who have taken circuit theory courses, right? That's the don't care condition. So what will be, therefore, my logic expression for this? Simple. H plus H bar A. Right? Then I am literally done actually, right? I have captured both the emotion and the physiological aspect of the brain. Now I have to go and simply make it, right? The making part is easy. How to implement this mechanism in hardware, right? So first of all, we need a tongue. We talked about tongue today in the morning, right? The tongue we already have with graphene, right? And the other thing is that we need is, it is only tongue, right? This is only taste, correct? There is nothing else is involved. But now there should be 2 pathways. The tongue should send the information through this hunger neuron to this physiological part, and through this appetite neuron through the emotional side of the brain, right? So therefore, I will show you how we are making this electronic tongue a little bit different, because right now it's not food sensing but also decision making. So I have to use 2 kind of sensors, and then I need to kind of convert it using this appetite neuron, and the hunger neuron, and put it to the gustatory cortex where this circuit exists. This is the circuit that implements this operation, H plus H bar A. That's really the connection between your emotional side and the physiological side. You see, that's what I have to do. So this is a NOT gate, right? This is AND gate, and this is an OR gate, right? You see the last operation is OR, correct? So this is where the H comes, the hunger neuron information comes straight, and then this is H bar, and then here it is your A, that A comes from this neuron, and then they make the decision. Correct? Okay? Rest is very easy. The memory register is used, I will come to that. I will come to that because it is programmable, because appetite is something that also depends upon your mood, right? And that you need to program, right? If you're in a good mood, you will probably eat that cheesecake. If you are not in a good mood, then leke jao bhai, abhi khana nahi hai. Huh? Yes.
So that is hunger intake and appetite, and this should be analog, right? Because there is an extent also. It's not like that.
There's a lot, right? I'm saying that this is the very first demonstration of integrating emotional intelligence, and you can build from that. You see, you can bring in a lot of other aspects as well,
like
right?
Yeah.
You can, the more complex you make that circuit, that's why we human beings are so complex, right? I know that you like a cheesecake, I bring it for you, I take it away. Because today you are in a different mood, maybe something else has happened to you, right? So this circuit, if I can use another input, right? Which could be your mood, correct? So I could simply add more and more, but I have to start building these neural circuits to bring both the psychological and physiological aspects. That's what I'm trying to show over here with a very simple example, right? And so then we use graphene, this have seen again, right? But now this graphene chemitransistor is another chip, okay? We don't care about, so this is all the details, different chip altogether. This is a graphene chemisensor response that we have already seen on the liquid on top. These all have been discussed, so which makes my life easier now, right? So you all know about this, how a graphene tongue works. So I simply gathered that information. But you see, this information is in current domain. But logic circuits only work with voltages, right? So what I have to do is, I have to, take 2 graphene devices. Okay, these are for different, coffee, tea, it's just, different responses. I use 2 graphene devices and connect them together. And in the middle node, I will get a voltage. Okay. Now here also, this device-to-device variation is very important, because if the 2 devices are exactly the same, and if I put a solution over there, right, will it matter what solution I put on this intermediate voltage? Tell me this thing, right? So this is a graphene chemi-transistor. This is another Giffen chemi-transistor. There is a voltage applied over here, voltage applied over here. What will be my VC? Tell me first, what will be my VC? Is there a mathematical expression for VC? This is not a NOT gate. This is just a voltage divider.
Okay. Looking very identical like inverter.
Yeah, but this has to be a P and this has to be an N in order for it to be an inverter. This is just a voltage divider. There is a gate. Even if it is not there, this is a resistor. This is another resistor. And there is a node over here. What will be the voltage over here? This will be VDD times, R1 divided by R1 plus R2. Right, that's what it is. Correct? Now, if I put solution A versus solution B, will this voltage change is what I am asking. Because it's the ratio of the two resistances, it will not. If the two graphene devices are identical. If two are exactly the same, yeah, right? So here also device to device variation comes to a rescue. Because since the two devices are different, right, then it will give you a very non-monotonic dependence of the VC with the gate voltage. Okay? If you do the math, you will find that, the neuron looks like this, and if you have a different solution like sugar versus bitter, you see that the response is different. So far so good, right? But this voltage information is because we have to use logic circuits. These are analog values. I have to convert this analog voltage into digital. Because the circuit that we did is a digital circuit. I need ones and zeros for that. Correct? So I take this analog information, right? And you can see that for different suites, the hunger neuron, as the solution concentration changes, this is the response of the device, and I can threshold it. Okay? And the thresholding part, let me just see. Okay, is hunger and this is satisfied, because I'm also bringing in one more aspect. How long you will feed will depend upon how long you are hungry, right? So once you have the food, as the food you getting consumed, the device response keeps changing, and after some time, you see that the response kind of goes from one state to the other. That time you are actually satisfied. You will stop feeding at that point of time, right? And I can actually do that even with the device, and you can see if it's a sweet substance, it feeds for longer. If it's a bitter substance, it feeds for shorter period of time. Because your hunger generally gets satisfied earlier if you're eating Karela sabji versus biryani, right? So that kind of is also captured in this device, okay? And the same is for the appetite actually, right? So after some time you don't have appetite. If I keep feeding you cheesecake after cheesecake, I will get very bored about eating more cheesecake, right? But I have known, during our father's generation, one person can use 40 rasgullas, 50 rasgullas. I cannot eat more than 2, then I will saturate, right? That's like appetite versus apathy. Like even if this is something you like, but after some time you will not like it anymore, right? So that is also kind of captured, okay, with this thing. And bitter is something for which you don't even have appetite. It's always apathy, right? But for sweet, you have an appetite after some time and then you don't like it, right? So this is also kind of captured using this device. So now once this is done, then we digitize this hunger and appetite neuron. And these are the circuits for analog to digital conversion. Okay, this is nothing but literally a comparator circuit. A comparator circuit simply compares with a given threshold. And you see this circuit has an output input characteristics like this. So anything below this point, it will be 0. Anything above this, it goes to 2. So that's like, logic 0 and logic 1. Okay, that's what we do. So we take that analog signal and convert it into digital spikes, right? The same thing, and this is a lot of details of the circuit. This is actually made using MOS2 devices, okay? And you can see that we are using a 4-stage cascaded inverter. This is actually an inverter circuit, and we cascade 4 stages, because if you use 2-stage, you see then it is like not like a very abrupt response, right? As you go to more and more stages, the gain of the inverter increases, and you become like a very sharp transition. Got this part, right? So this is a comparator that we built. Okay. So therefore, all this information which were kind of in the analog domain, because they're continuously changing and they are in the range of 0.1 to 0.3, now get converted into digital signals, right? And once we have the digital signals, right, then it's very easy. Then you make these circuits. These are also possible to make AND gate, OR gate, logic gates, right? You put the information in there. So now you have sweet and bitter, right? And then this is your H bar. This is your A, this is your H bar A, and this is your feeding. You can see that if it is sweet, you feed for longer. If it is bitter, you feed for kind of lesser, right? So that was our ultimate objective, is to bring in. And this involves both the emotional and the physiological factor, right? And then this is also, we are using an MEM transistor, the question that you asked, because using the MEM transistor, I can change this comparator voltage. If somebody has sugar, then they will probably only eat one cheesecake and then they will stop, correct? So that can also be programmed. So for each individual, you can program what is the threshold of their hunger. And even some people have more hunger and some people have less hunger. That results in whether you are this or this. No? Right? So that can be captured using these programmable devices. That's why we are using this programmable MEM transistors for this. And I think programmability I have already explained, right? This was from previous lectures, right? We have already talked about that. And the potential application of gustatory circuit, right? This guy keeps feeding for long, right? Sweet, leads to diabetic, right? And you can show that, it's just that how long you feed can also be programmed. The longer you feed, more you become like that person. Okay? So the conclusion is that, so this is the first time we have been able to develop a circuit which takes into account the emotional aspect, and then we are trying to kind of combine this graphene chemisensor and MOS2 based. So our gustatory cortex is now also made out of MOS2 devices, and then the tongue is graphene. So tongue is graphene and gustatory cortex is MOS2 transistor, and this is that demonstration. Okay, very simple, but a little bit going into a different trajectory compared to the typical neuromorphic computing devices. Okay, any questions on this? These are short lectures.
During runtime, how can we program the transistor?
Not during runtime. You can program it before or after, right? You can set the state of the device. It's almost like before you go for eating, you know what your mood is, so that will determine how much you are going to eat, right? So that's what I mean. Where is the application of this? Many places, right? I mean, if you think about the next generation of restaurants, they're probably going to use this kind of tricks, right? If they know what you like, they will probably make sure that the smell of the food that you get, the texture of the food that you get is according to your liking. This is already happening actually. A lot of advertisement, I mean, in fact, McDonald's have started doing that. This is something called some neuro advertisement or something. They know what kind of smell will bring you inside the shop. And they will ensure that the fries they are cooking actually gives out that kind of a smell. Okay? So they are playing with your emotion. And you, without knowing, right, you are getting dragged towards. Because, they have all the information. What kind of food you search for, what did you like to do, what are you eating, all information is there for Google. So they just have to learn their machine learning model. In fact, I feel like today Google knows about us more than even we know ourselves. So they can even start playing with your subconscious, and this is like making their life easier. So, but I can't help. Okay, thank you.